Have you ever really thought about what's going on when a nail rusts, or why that bag of chips you forgot about now tastes, well, terrible? It's not magic, it's chemistry. And in this explainer, we're going to decode the secret language of chemical reactions. We'll uncover these hidden patterns that run everything from a firework display to the very air you're breathing. So, let's dive right in. Okay, to get us started, I want you to picture a really simple experiment. Imagine taking a clean, shiny little ribbon of a pure metal, something like magnesium. You grab it with a pair of tongs and you stick it in a flame. What do you think is going to happen? You get this, an absolutely blindingly bright, dazzling white flame. Seriously, it's so intense it's actually harmful to stare at directly. It's an incredible show for sure, but it leaves us with a big question. What is actually happening inside all of that light? So, what is the science behind that incredible light? Well, that's what we're here to figure out. We're going to break down exactly how that simple metal ribbon transforms into something completely new, a white powder called magnesium oxide. But, before we can start solving these chemical mysteries, we kind of need to learn the language. Chemists have a special way of describing these changes, a language of symbols and formulas that lets us map out exactly what's going on. And that language is the chemical equation. It's actually a beautiful, simple idea. On the left side, you've got your starting ingredients. We call those the reactants. Then you have an arrow showing the change, and on the right side, you've got what you end up with, the products. It's basically the universe's most fundamental recipe card. Now, here is the single most important rule in all of chemistry. Seriously, the law of conservation of mass. All it means is that you can't just create or destroy atoms out of thin air. Whatever atoms you start with on the reactant side, you have to end up with the exact same number and type of atoms on the product side, no exceptions. And that is exactly why we have to balance equations. It's kind of like a logic puzzle. We use what's called the hit and trial method, which is just a fancy way of saying we tinker with it, adding numbers in front of the molecules until the atom count is precisely the same on both sides of the arrow. All right, let's just walk through one together. Here we have iron reacting with water to make a type of rust and some hydrogen gas. So first, let's do a quick head count. Left side, 1 iron, 2 hydrogens, 1 oxygen. Right side, 3 irons, 4 oxygens, 2 hydrogens. Yikes, not even close. Okay, let's start with the oxygen. We'll put a 4 in front of the H2O on the left. Great, now we have 4 oxygens on both sides. But wait, that messed up our hydrogen count. Now we have 8 on the left and only 2 on the right. No problem. Easy fix. Let's put a 4 in front of the H2 on the right. Now our hydrogens are balanced. And finally, the iron. 3 on the right, only 1 on the left. So we'll just pop a 3 in front of the Fe on the left. Let's do one last check. And it's perfect. Everything matches. The equation is balanced. So now that we've got the language down, we can start to see that pretty much all of the millions of chemical reactions out there actually fall into just a few main categories. I like to think of them as reaction families. They all follow some pretty recognizable patterns. And this is a fantastic little cheat sheet for those families. You've got combination, where things come together. You've got decomposition, where one thing breaks apart. And then you've got displacement reactions, which are all about swapping partners. Let's take a closer look at each one. First up, the combination family. It's exactly what it sounds like. 2 or more simple things, let's call them A and B, come together to form one new, more complex thing, AB. A perfect example is when quicklime reacts with water. They combine to make a single new substance, slaked lime, and man, does it release a lot of heat when it happens. Next up, we've got the total opposite, decomposition. Here, a single complex compound breaks down into simpler pieces. So instead of A plus B making AB, we have AB breaking apart into A and B. And for this one, we've got a fascinating example to look at. All right, another little mystery for you. You take these really pretty green ferrous sulfate crystals and you start to heat them up. The first thing you notice is they turn white. But if you keep heating them, they do something even more dramatic. They turn into this brown, kind of earthy-looking solid. So what on earth is going on here?
What you just witnessed is a classic case of thermal decomposition. The heat energy is literally tearing that ferrous sulfate molecule apart. It breaks down into that brown solid, which is basically just rust, in two different gases that have a really sharp smell, kind of like a lit match. And this isn't just a lab trick, it's how an airbag in a car works. One compound rapidly decomposes into nitrogen gas, and boom, the bag inflates. One reactant, multiple different products.
Okay, let's move on to our third family, displacement reactions. The best way to think about this is like a dance. If a more popular, or in chemistry terms, a more reactive element shows up, it can just cut in and steal the partner of a less reactive element.
And here is the perfect visual for it. You start with a plain old iron nail and this really bright blue copper sulfate solution. You dip the nail in, you wait a little bit, and look at what happens. The blue solution has faded to a light green, and the nail is now covered in this reddish-brown stuff.
So what happened? Well, it turns out iron is more reactive than copper, so the iron atoms basically muscled their way in, kicking the copper atoms out of the solution. The iron dissolves, forming that new light green stuff, which is iron sulfate. And those now homeless copper atoms, they just plate themselves right onto the nail, creating that reddish-brown coating. Pure displacement in action. Now let's go one layer deeper. Because underneath a lot of these reactions, there's this invisible exchange going on, this fundamental process of giving and taking that really powers so much of chemistry. We call it redox. Redox is short for reduction and oxidation. And here's the thing, they are a package deal. You can never have one without the other. It's all about the transfer of these tiny particles called electrons. Here's a little trick to remember it. Oil rig. Oxidation is loss, reduction is gain. Of electrons, that is. This simple exchange is the engine for countless reactions. So in a redox reaction, you always have one thing losing electrons, we say it's oxidized, and another thing gaining them, we say it's reduced. In this example here, when zinc oxide reacts with carbon, the carbon literally steals the oxygen away from the zinc. The carbon gets oxidized and the zinc gets reduced. It's a perfect invisible little transfer. Okay, so why does any of this actually matter? Well, because once you understand these patterns, I promise you, you will start to see them absolutely everywhere. These reactions aren't just happening in some far-off lab. They are happening in you and all around you all the time. Remember that powerful process, oxidation? Well, you know it as corrosion. That's what's happening when iron is slowly attacked by oxygen and turns to rust. And you've definitely experienced it as rancidity. You know that stale, just awful taste of old chips or nuts? Yep, that's the fats and oils being oxidized. But here's the really cool part. Understanding the chemistry means we can fight back. We know oxygen causes food to go rancid, so what do? We get rid of the oxygen. That's why chip bags are filled with nitrogen gas, and it's why putting your leftovers in an airtight container keeps them fresh. It's simple but incredibly practical chemistry. So, I'm going to leave you with a little challenge. You now have the tools to see the world like a chemist. The next time you see leaves changing color, or you strike a match, or you even just take a breath, stop and ask yourself, what is the unseen chemical dance that's happening right in front of me?